Welcome back to the lectures on quantum chemistry and molecular spectroscopy. We shall continue to solve the assignment 1. There are some more problems left. The problems 8 to 12, at least I will give you hints on how it should be solved. Okay. So, let us go to problem 8. The problem 8 asks you to calculate the expectation values, or what are called the average values of the operators for position x, x square, which is the square of the position operator, p the momentum, and p square the square of the momentum for a particle, free particle in a 1D box, and the eigenfunction is given to you as square root of 2 by L sin n pi x by L. Also it asks you to calculate the uncertainty product known as the delta x delta p, which is defined as given here, and verify the Heisenberg's uncertainty principle. Let us recall the definitions. The expectation value of any operator A in the basis psi is psi star A psi d tau divided by psi star psi d tau. So, in the case of a particle in a box, the position operator, the expectation value is, there is a root 2 by L, but the function wave function is multiplied by itself. So, you have 2 by L 0 to L sin n pi x by L. This is in the state psi n, x times sin n pi x by L dx. The denominator is 1 because the wave function is normalized. Therefore, what you have is 2 by L integral 0 to L x sin squared n pi x by L dx, and that would be 2 by L times 1 by 2 0 to L. You write the sin squared in terms of the double angle formula 1 minus cos 2 n pi x by L dx. So, that gives you 1 by L times 2 integrals, namely 0 to L x dx minus 0 to L x into cosine 2 n pi x by L dx. It is straightforward to show that this integral is 0, okay, because you can write this as x into d of sine 2 n pi x by L times L by 2 n pi, if you write this as a partial derivative between 0 to L, and that is given as x times, this is a u dv formula, therefore uv x into sine 2 n pi x by L times L by 2 n pi uv between the limits 0 to L minus v du, which is 0 to L sin 2 n pi x by L dx. Okay. This is 0. This is 0 because at x is equal to, at 0 x is 0, at L sin 2 n pi x is 0. So, this is 0. Therefore, that integral is 0. So, if you go back, you would see that there is only one integral, namely 1 by L 0 to L x dx, and that is given as L by 2. So, the average value of x is L by 2, the average value of x square is obviously L square by 4. Okay. So, that is known. The calculation of the average value of the square of x, this is the average of the position squared, this is the square of the position, and this is given by again 2 by L integral 0 to L sin squared n pi x by L x square dx. Again you can do this using the partial integration with the u dv type formula. So, if you have to do the integral sin squared n pi x by L x square dx, 0 to L is integral 0 to L x square d, sorry, it is a you again split this into two terms, namely 1 by 2 1 minus cos 2n pi x by L, like what you did dx, and the first term gives you x squared dx by 2. So, it is x cube by 3 and there is a 2 by L in front of it. So, if you put the 2 by L here, you have 1 by L, and then this is x squared dx will give you x cube. So, it is L cube by 3 minus the integral 1 by L 0 to L x squared cos 2n pi x by L dx. This has to be done in two steps like what I did in the first step. Therefore, I will give you the answer, namely it is L square by 3 minus L square by 2n square pi square. Okay. This is the final answer for this. This is the integral or the average value squared, that is the average value of the square of the position. The average value for the momentum for the particle is 0. During the lectures we have mentioned this and we calculated it, and the average value for the square of the momentum is, if you recall, it is 2 m times the average value for the energy, and the energy for this particle at this state is given by h square n square by 8 m L square. So, you get h square n square by 4 L square. So, that is the p squared average. Therefore, now let us get the delta x, delta p. If you take the square of this, that is equal to x squared average minus x average squared multiplied by p squared average minus p average squared. Okay. This will be L cube by 3 minus L square by 2n square pi square that we calculated, and the x average square is minus L square by 4. So, this is the delta x squared, and the delta p squared is simply h square n square by 4 L square. Okay. So, the L goes away from all of this, and you remember it is 1 by 3 minus 1 by 2n square pi square. Okay. It is minus 1 by 4, so it is 1 by 12. Okay. 1 by 12, and then you have h square n square by 4. Okay. Now, you can see that this is greater than or equal to h by 4 pi. Remember, the difference is the largest here when n is 1, the smallest state. For all other n's, this is greater than the n equal to 1 value. Therefore, this term keeps on increasing, and this term also keeps on increasing. Therefore, the smallest value is obtained when n is 1, and when n is 1, you have 1 by 12 minus 1 by 2 pi square times h square by 4, which gives you roughly a number close to this, but greater than this number h by 4 pi. Okay. It's easy to just numerically you can check this out. Okay. It is greater, not greater than or equal, it is greater than h by 4 pi. Therefore, the smallest uncertainty which is obtained for n equal to 1 is already greater than h by 4 pi, and for all other values of n, both these terms are increasing. Therefore, they will be definitely much greater than h by 4 pi. So, this is Heisenberg's formula. I think that is what we wanted to verify in that problem. Yeah, show that this verifies the Heisenberg's uncertainty problem principle. Okay. In the lecture itself, we will see that why this is the formula for the uncertainty, but we given this as the uncertainty, how do you calculate them is what I explained in this problem. The next problem says for the free particle in a two-dimensional box, we have to calculate the expectation values for the product of the position coordinates x and y, the product of the square of x, the average value for the square of x, the average value for the square of y, and then a particular peculiar quantity which is like minus I h bar x dou by dou y, y dou by dou x. If you look at it carefully, this will be x p y minus p y p x times y. It will be a cross product of position and momentum. So, it is something like an angular momentum, and we will see that the answer is actually 0 okay, for that. Let us look at the particle in a 2D box. So, 2D box, you recall that the formula for the wave function psi is given in terms of two quantum numbers n1, n2, and in terms of the two coordinate variables x and y, and that is 2 by L sin n pi x by L sin n pi y by L. Therefore, if you calculate any average value A, you have to do the following integral, namely psi n1 n2 x comma y. Star is not needed because these are real functions. Then the operator A acting on the function psi n1 n2 x y, except that now the integral is over both dx and dy, because x goes from 0 to L and y also goes from 0 to L for a square box. Okay. So, this is the quantity we have to calculate. The denominator is 1 because the wave functions are normalized. So, if you want to calculate the average value x y, if you put x y here, the operators, because they are all operators in quantum mechanics. Okay. If you put x y here, you see that the integral is expressed in terms of functions, products of x and products of y. This is also a product of x and y, and so is this one. Therefore, the integral separates out into two integrals, namely 0 to L, keeping 2 by L outside, sin n pi x by L. I should say this is n1 and this is n2. Okay. So, n1 pi x by L x operator times sin n1 pi x by L dx. This is one integral for the x, this is the other integral for the y, 0 to L sin n2 pi y by L, the operator y sin n2 pi y by L dy. So, it separates out into two integrals, x only integral, y only integral. Okay. And if you have to write this as 2 by L and 2 by L, then you know exactly that this is the particle in the one dimensional problem for the x coordinate. Therefore, the answer for this is L by 2. The average value for the position of the particle is L by 2. And this is, except for a coordinate change, this is also a particle in a one dimensional box with the coordinate y. This also is L by 2. Therefore, the average x y is L square by 4. Okay. It's easy. So, separation of variables and separation of the functions as products of functions of one variable times products of functions of another variable helps you in also separating out the average value calculations as one dimensional integrals. And such things are important in mathematics and physics and also in chemistry. When you calculate more and more complicated system properties, it is important to see the separability of these integrals as much as possible. Okay. This is just an illustration to do that. What about the quantity x square, the average value x square for the state psi n1 n2? It is also easy. You can see it immediately that this integral is 2 by L 0 to L dx sin n1 pi x by L x square sin n1 pi x by L. This is one integral from the x part of it and the other integral does not have the operator, it is 0 to L sin n 2 pi y by L sin n 2 pi y by L dx, because this operator x square obviously acts only on multiplies the x square or any function which is dependent on x, and therefore, the integration is done with the x variable only. This you already did in the previous problem. You calculated this, as you recall, the answer was L cube by 3 minus there is this L square by 2 n square pi square. Sorry, this also should be L square. This is x square, so this should be L square. So you calculated this. This is of course a normalization integral. So this is equal to 1. So the average value of x square in this function does not change, in this representation does not change. In a similar way, the average value of y square, all that you do is you associate y square with this term, there is no x square here, and therefore this is a normalization integral, and this will give you exactly the same result. After all, the integration, sorry, this integration variable is dy. Yeah. The integration here will be x with no function, and the integration with y contains the y square if you want to calculate the average psi n1 psi n2 is identical, and the answer is also the same. Okay. The last one is this quantity, expectation value of minus I h bar x dou by dou y minus y dou by dou x. Okay. Recall that minus I h bar dou by dou y is P y, and minus I h bar dou by dou x is P x. Therefore, this integral is x P y minus P y x. The average value, that is what you wanted to calculate in the state psi n1 n2. You see that this is x only, this is y only, therefore, you can see that the first term x P y will be 2 by L sin n pi x by L x sin n pi n1 pi x by L dx. This is the x part of it, and then the y part is 2 by L sin n2 pi y by L, and P y is the derivative minus I h bar d by dy sin n2 pi y by L dy, and the limits are 0 to L for the square box. Okay. Then you know that this is nothing but the average value for the position, which is L by 2. This is the average value for the momentum in the coordinate representation corresponding to the wave function, and therefore, this is 0. The average value for the momentum is 0, so as the previous problem. Therefore, x by P y is 0, and likewise this is also 0. There is no angular momentum. The plane of motion does not contain, the two-dimensional box motion does not lead to any other motion like an angular motion and so on. There is nothing called, this is called the angular momentum in two dimensions, and the direction of the angular momentum is perpendicular to the plane, but this is 0 for the particle in the 2D box. So, this is problem 8. Problem 10 is a conceptual, it is an introduction to a concept called the linear combination of wave functions are also acceptable in quantum mechanics as wave functions. So, what we have here is an arbitrary normalized wave function for a particle in a box is given by this formula x square into L minus x square, and we are asked to find out the normalization constant C. And secondly, we are asked to express this wave function as a linear combination of all eigenfunctions of the particle in a one-dimensional box. Okay. root 2 by L sin n pi x by L is the eigenfunction with an eigenvalue E n, and it asks you to obtain an expression for the coefficient C n, and also what is meant by the absolute square of C n summed over all such n's, and finally what is the average value for the energy of the particle in the state. The concept in this problem is general for all of non-relativistic quantum mechanics, therefore please try and understand this very carefully. Okay. First of all, we write the wave function psi of x is equal to C x square into L minus x whole square. Now, it is acceptable because it is normalizable. Second, boundary conditions are valid. What is the boundary condition? Psi of L and psi of 0, they both should be 0, okay, which is true in this case. Therefore, this function satisfies the boundary condition. It is an arbitrary function. If you ask h on psi of x, it will not give you an E on psi of x, it will give you something else, because this is a second derivative. Remember, it is d square by dx square, the minus h bar square by 2m, and that will act on x square into L minus x square. This is a polynomial, so it will give you a reduced polynomial, it will not give you the same function. Therefore, this is not an eigenfunction. This is called an arbitrary state, which we do not know what it is. But if we try to measure the energy associated with the state, we will get one of the eigenstates which the particle in the box tells us as the result, and those eigenstates, eigenvalues are h square by 8 ml square, 1, 4, 9, 16, 25 and so on. So, when you make a measurement, you will get only one of them. But unlike other regular measurements where you expect the same result for the same measurement for the same system, you will not get that here. If you make another measurement on an identical system, you may get a different eigenvalue with a different probability, and that is not different in a sense that you have a coin with two states, head or tail. Every time you throw the coin, you do not necessarily get head all the time, you get head sometimes, you get tail sometimes, not both, one or the other. And if you have a die with 6 faces, when you throw the die exactly the same way each time, you do not get the same result, you get different. So, there is nothing special about that part of it, that this is not an eigenfunction. Therefore, when you make a measurement, you get a different energy eigenvalue each time you make a measurement. How do we incorporate that in our description of the particle, of the state of the particle? That is what this is when we say C x square into L minus x whole square be expressed as a linear combination of all eigenfunctions C n root 2 by L sin n pi x by L. So, this problem is to suggest that any arbitrary state can, in repeated measurements, if you have n number of copies of them, infinite number of copies of them, each one of them can give a different eigenvalue when an energy is measured, and therefore, what is the probability that we get a particular energy when we make the measurement? That information is contained in this coefficient, not in the coefficient itself, but in the square of the coefficient. Okay. This problem illustrates that idea. Okay. Let us first of all normalize this function. Okay. So, the normalization essentially means psi of x square, because these are all real, 0 to L dx, we want that to be 1, which means it is going to be c square x raised to 4 into L minus x raised to 4 dx should be 1. So, if you expand this, c square times integral x raised to 4, it is L raised to 4 minus 4 L cube x plus 6 L square x square minus 4 L x cube plus plus x raised to 4 dx is equal to 1. Okay. It is a fairly simple integral to do, except that there are numerous terms. The first term is, for example, the first term 0 to L is the limit 0 to L. The first term is x raised to 4 L raised to 4 dx, and that is L raised to 4 times x raised to 5 by 5 between the limits is L raised to 5 by 5. Okay. So, that is the first term. The second term, for example, is 4 L cube times integral x raised to x raised to 5 dx between 0 to L. So, if you calculate this, this is x raised to 6 by 6 between the limits, it gives you 4 L cube by times L raised to 6 by 6, 3 by 2, 2, 2, 3. Okay. So, likewise you can calculate all the individual terms and you just add all these fractions. Okay. When you do that, the answer turns out to be c square L raised to 9 divided by 630, that will be 1. That is the answer you will get when you do the arithmetics. Therefore, c is square root of 630 by L raised to 9. What is special about L raised to 9? Why is it right or wrong? Look at the function c x square L minus x whole square. This is position. So, the unit here is, say, distance or meter or whatever it is. So, let us write this in the form of meter. So, it is meter square, and this is a meter also square. And when you take the integral psi squared dx, you are integrating over the position. So, you are integrating over quantities which are meter 4 times meter 4 times a meter times some number, that is equal to 1. Okay. Therefore, the normalization constant c square must have the inverse of this dimension in order for the integral to be a number with no physical dimension associated with that. Therefore, the dimension of c should be the square root of it 1 by the square root of this. Therefore, it should be 1 by the length to the 9 by 2. This is also a fundamental result in quantum mechanics, that if the wave function depends on a position variable in one dimension, the wave function dimension will be 1 by square root of the length. You have already done that, because you see the particle in the 1D box, you have 2 by L sin n pi x by L, square root of L in the denominator, L to the half, distance length to the half. So, if it is a 3-dimensional wave function, for example, for hydrogen atom, you have r theta phi, 3 coordinates are there. Therefore, you see the integral is r square dr d theta d phi sin theta. So, the volume element is length cube, and the wave function is wave function and it is a square. Therefore, the wave function square must have the dimension of length to the minus 3. So, the wave function should be 1 by L to the 3 by 2. So, the dimension of the problem, if the dimension is n, the wave function should have the unit 1 by L to the n by 2. Okay. That is what that is. This represents, therefore, the normalization constant, that is root 630 by L raised to 9, should be understood with not only the number 630, but why the number of the power of L being 9 inside the square root should be associated with the integrals that you do. Problems tell you many more things that cannot be told in the lectures. Therefore, it is very, very important that you solve these problems and you analyze them in greater detail. Okay. Now, let us continue to the second part. We write psi of x, which is, now we have normalized it. So, 630 by L raised to 9 x square into L minus x whole square. We want to write this as a sum over n of all wave functions, a numerical coefficient C n, which we do not know what it is, root 2 by L sin n pi x by L. Okay. So, how do we find out Cn? It is very simple. Sin n pi x by L root 2 by L, they are all normalized wave functions, they are also orthogonal. For example, this is nothing other than C1 times root 2 by L sin pi x by L plus C2 root 2 by L sin 2 pi x by L plus etc. plus infinity Cn times root 2 by L sin n pi x by L, and it continues, and you have psi x here, okay, which is that, namely this number, this function. So, suppose you multiply this integral, the left hand side, with sin pi x by L and a root 2 by L, and you do psi x, multiply this, and then integrate between 0 and L dx. Then you see on the right hand side, the first term gives you C1 2 by L integral sin squared pi x by L dx, okay, which you know is nothing but normalization, therefore is equal to 1. What about the next term? It is C2 2 by L integral sin pi x by L sin 2 pi x by L dx between 0 to L plus other terms. Likewise, all the other terms. You multiply every term with the sin pi x by L, square root 2 by L, and then you do the integration. The first term gives you C1. What about the other terms? You remember that these wave functions are orthogonal to each other. Therefore, sin pi x by L is orthogonal to the sin 2 pi x by L, goes to 0. What about every other term? All of them go to 0. Therefore, the general formula Cm is integral 0 to L psi m of x. If it is complex conjugate, if it is a complex function, you should always have a star. Sorry, this is not psi m star. This is root 2 by L sin m pi x by L star, actually, because that is what we should be doing, but anyway the star is the same as the without it, psi of x dx. Therefore, this m orthogonal function, orthonormal function, picks the coefficient or projects the wave function to give you that coefficient Cm. So, the general expression for Cm is therefore integral 0 to L root 2 by L. So, let me also put the other factor, namely 630 by L raised to 9 0 to L dx sin n pi x by L multiplying the psi of x, which is x square into L minus x whole square. That is the exact formula for Cn. There are two more parts to this problem. Let us finish this and then we will sum up this part of it. The other problems will be done in the next part. The next problem is, what is the sum Cn squared? Okay. Now, the wave function you know is given by this formula, namely root 630 by L raised to 9 x square into L minus x whole square. This is normalized. Psi of x, so that psi of x square dx between 0 to L is 1. Okay. And on the right hand side you have sum over n equal to 1 to infinity Cn root 2 by L sin n pi x by L. Okay. Therefore, this also should be normalized in the sense that if you take this function sum over n equal to 1 to infinity Cn root 2 by L sin n pi x by L, this is an infinite sum, and therefore, the next infinite sum, that is the psi star psi, we shall write this as m equal to 1 to infinity C m root 2 by L sin m pi x by L dx 0 to L. That is what this term is, psi x square, this one sorry, the psi x square dx 0 to L is psi x square 0 to L, okay, 0 to L. Now, you can see immediately that when you expand the right hand side with these two functions, one is n pi x by L, the other one, this goes from 1 2 3 to infinity, this also goes from 1 2 3 to infinity. If you take the one function sin pi x by L, the only one that will survive this integral here is the other function, namely sin pi x by L. Therefore, this term will turn out to be this, the sum will be 0 to L 2 by L C1 square sin pi x by L square dx plus 0 to L C2 square sin squared 2 pi x by L 2 by L dx plus etc. No cross terms will be possible. Cn, Cm, where n and m are not the same. Remember that sine functions are orthogonal to each other, therefore, that integral is 0. So, no cross term exists. Therefore, and each one of these terms itself gives you only the coefficient C1 square, because the rest of it is equal to 1. The wave functions are normalized. Therefore, the eigenfunction expansion gives you the orthonormal eigenfunction expansion of any arbitrary function, gives you sum over n C n square is the normalization of that function psi x dx 0 to L, and that is 1. Therefore, the sum over n C n square is 1. Therefore, the quantity C n square divided by the sum over all of them C m square, all of them, gives you the probability that the state of the system when measured for its energy, gives you the energy E n. This is a probability, and the probability is different for different n, and the state itself will become root 2 by L sin n pi x by L. The probability that the state psi of x, which is arbitrary, it is a combination of all of them. But when you measure, what is the probability that you will get this eigenstate with this eigenvalue, that is given by the square of the coefficient. Therefore, that is the interpretation for the linear combination coefficient. The coefficients are not important, they give rise to what are called the probability amplitudes and interference, but the square of the coefficients tell us about the probabilities for the results, the outcomes, the measurement of the state for a given energy, given eigenvalue, given eigenfunction, and so on. Okay. That is the interpretation for this. Now, you know immediately you can verify that the average value energy for this system, since the probability is C1 square for the state 1, and when it is 1 the energy measured is E1, you can see that the probability for the energy 2 is C2 square, the probability for energy 3 is C3 square, and so on. Therefore, the average value is n equal to 1 to infinity C n square. Okay, I have just put the C without the absolute values, but they are the absolute values times E n. This is the average value. And now you can see if it is an eigenstate, then all coefficients are 0 except 1, and that means it is that energy. Therefore, the energy measured for an eigenstate is always the eigenvalue. If it is not an eigenstate, any one of the energies are possible, and the probabilities with which these happen are given by these coefficients. Therefore, this problem is extremely important in understanding the conceptual generalization of a simple eigenvalue eigenfunction problem of a particle in a box, the arbitrary wave function, the normalization of an arbitrary wave function, and the expansion of an arbitrary wave function in terms of the basis or the eigenbasis. All these concepts are tied up in this one problem. We will continue with the remaining problems in the next part.